Good morning. This is our recorded lesson for Friday, August 21st for IED. As of the recording of this, I have your team in Teams, but I am not an owner of the team in Teams, so I cannot schedule a meeting. If that changes before tomorrow morning, I will schedule a meeting and you will be expected to log in. So if you're watching this through a video link in Focus, please make sure you go and check Teams, make sure that there's not a live meeting happening. As a reminder, you need to check your attendance form and you need to do it during the actual class period. You need to be logged into Teams for period 1 during period 1. So that is between 7:15 and 8:05. So you have that window to make sure that you are sending me your attendance form in. If you send it in later, you will be marked absent for the class. Just like if you showed up to physical school late, you would be marked absent for first block. So this is your reminder. Make sure that you check that. So the topic for today's lesson is an introduction to the design process. And what you're going to see on these slides is a lot of screenshots from things that come from inside the PLTW curriculum. I will read some of it, I'm going to paraphrase some of it, and we'll work through the material. After the video lesson is over, if I am able to be live in Teams, then we'll do a little Q&A. Otherwise, we will be done. So what is a design process? And notice the indefinite article there, a design process. A design process is any systematic series of steps used to solve a problem or accomplish a task. The key thing about it is it's systematic. You move from one step to the next in your endeavor to solve a particular problem. There are many different design processes. There's not like a right one or a wrong one. So that's what we're talking about. Like, you're given a problem, how do you go about solving that problem? As a career connection, professionals in nearly every industry and academia apply a design process to solve problems and guide the design and innovation of products and processes. As an educator, every time I do a lesson plan, I am engaging in a design process. What do I want my students to know? What do I want them to be able to do? How am I going to get them from where they are to where I want them to be? And how will I know if they get there? How does a teacher know if they need to go back and reteach or explain something again? And so as a teacher, we go through this design process all the time. And as we'll look at the PLTW design process, it's not necessarily linear, nor is the teaching process. It's not linear. There are lots of times where I have to back up. I have to do something over again. I have to reteach a different way. And you'll see that as we go through the curriculum this year, that what maybe was in my process at the beginning of a lesson isn't what we end up doing at the end of the lesson. Okay, so how does the design process factor into this course? You're in a course called Introduction to Engineering Design, and there are a couple of really key skills that come into play in engineering, in IED. Okay, something paused in the recording there, so I hope there's no glitch in it. Like, my screen gave me the circle of death. Hopefully there's no glitch in the recording process. I hope not. So two of the key skills covered in IED is use of a specific design process and then how to document the process in an engineering notebook. Those are two of the skills you want to come out of this course with, and they're very transferable skills. Being able to solve problems and being able to document and communicate how you've solved that problem is applicable in so many different subject areas and real life situations. Some of the other skills involve the computer-aided design, the CAD program, which will be Fusion 360, and then a culminating project, which is an automata. We didn't finish that project last year because we went online. So hopefully this year will be different. The goal here is to think like an engineer, is to train your brain to be able to process and solve problems a particular way, which is what a lot of education is. This will be valuable in all your classes. And while we obviously want designs to be successful, that is not the main goal of most of the activities and projects that we do. Clearly, we want things to be successful. In my role as a math teacher, I want my students to be able to get the right answer. But that's not all I'm interested in. In fact, I might be more interested in them having a wrong answer, but with really solid thinking behind it, and have like maybe a careless mistake. They left out a decimal point. So we do want our designs to be successful, but I don't want you to fall into this trap of thinking that you have to have this awesome design in order to be moving forward in how you're thinking and growing as a young engineer. PLTW, again, that's Project Lead the Way, has a specific design process that they have adopted for their curriculum. It's just one of many possible ways to solve problems, but for consistency, we pick a design process and we get good at it. This lesson will take you through the steps in the design process and introduce you to the first activity of the year. So today is a day that I would consider a lecture day. I will have you write some stuff down, so if you need to pause the video at this point and grab a notebook, just so you have something to write down some ideas in, that's fine. So an overview of the process. If you were in class yesterday, in our face-to-face class, you received a handout with this graphic on it. Have it handy and make supplemental notes on it as needed, so this would look familiar. If you were not in class yesterday, I do want you to pick this handout up when you come to class on Monday, because I would like you to have a handout that will have the design process in front of you. Note that the process is not necessarily linear, so we're going to use a little bit of a math term here. Linear would mean in a straight line. Oh, I thought I could. Oh, okay. That looks kind of cool. All right, that's not what I meant to do, but it's like in a straight line, meaning you move from step 1 to step 2, step 3, and so forth. The design process is not necessarily linear. This is like slowing way down. Crud. It's not necessarily linear. So you might move from step 2 to step 3 to step 4 back to step 3. You might like move and have to go back to the beginning. It can be a little bit messy. The steps can overlap each other. So it's a little bit more like a squiggle than a straight line. Step 1 in the design process is the definition of the problem. Problems exist everywhere, and they vary in their degree of complexity and importance. An acceptable problem is one for which there is no known solution, or one for which there is a solution that can be significantly improved upon. It must be valid, that is, not a problem because you say so, but because other credible sources agree that it is a problem. And justifiable, that is, the effort to solve the problem is warranted based on need and cost. So we've got two factors there. We want the problem to be valid. Okay, I'll underline that. I've never done this before. I don't know if it's going to work. Hope it does. Valid. So a credible source, there has to be an agreement that this is a problem. In the context of class, I am your credible source. If I tell you that this is a problem that needs to be solved, then it's a problem that needs to be solved. The other thing it needs to be is justifiable. In other words, is it worth it? Is it worth the time, the effort, the expense to solve the problem? Or is it not worth it? Is it a problem that we could, in theory, live with? And that's something that a teacher is probably going to always tell you that, yes, the problem is justifiable. Students don't always agree that a problem is justifiable. And there are situations where you might decide that, yes, you have a math homework assignment, but you also have something else going on, a family emergency, whatever it may be. And so you decide it's not worth the time because your attention needs to be somewhere else. So you get this idea that you have to have these two qualifications. Now, they give you some questions here. Who says it's a problem? In this class, if Ms. Taylor says it's a problem, it's a problem. What are the needs and wants of the stakeholders? This is something that we actually do see in education. Stakeholders are the people that have a stake in the problem being solved. So if we were talking about the school dress code, students would be stakeholders. That affects you. When we talk about education in general, parents become stakeholders. So what are the needs and wants of the people whose lives are going to be impacted by the solution of the problem? Are there prior solutions to the problem? Have people attempted to do it before? And this is where your phone can come in really handy, or computer, laptop, tablet, whatever you have if you're doing it from home, is you might look up who has tried to do this before under the constraints that I have, and look at that. Is the problem worth solving? And then this last one down here, what are the specific criteria and constraints required within the problem? Those might be in a classroom setting. Those are the requirements that the teacher puts on you. Your poster must be this size. You must have this many sources. You have to have this many pictures, and so forth. In the activity that we're going to do, I'm going to put some constraints on you. You are going to be allowed to modify some of the materials, and some of the materials you will not be able to modify. You're going to have to be able to launch your block without physically touching the block at the time of the launch, and so forth. Step 2, generate concepts. Once you have generated multiple possible solutions, you need to narrow your efforts to one or a few solution paths, or to one path. It is often difficult to truly conclude this step of the process because you could research and brainstorm indefinitely. At any point in the process, it may be necessary to adjust the problem statement and start over with a new problem statement. So once you've been given a problem, now you need to generate some ideas for how to find it. And this is where a lot of students really struggle, is not so much generating a concept. It's generating multiple concepts, looking at the materials you have, looking at the direction of the problem, and not locking in to the very first idea that you have. Students tend to have an idea, and that's what they want to go with. So an important part of generating concepts is this idea of brainstorming. So some things that you want to do as you generate concepts. You want to research the problem. Find out if somebody has done work on this problem before you. And that is totally fair game in the engineering world. If I ask you, I don't know if it's in the curriculum this year, but last year we had an activity where my students were given, I gave them 2 blocks and cardstock. And they had to build the biggest bridge between the blocks that they possibly could. And that was all they had to work with. And there were constraints on it, like it couldn't touch the desk. It couldn't, it had to be, they couldn't modify the blocks and so forth. But it's totally okay to go online and say, who else has had to make a bridge out of cardstock? You want to research the problem. This can become difficult. This second one here, brainstorming possible solutions. When you're brainstorming, you do not censor anything. No matter how ridiculous, if you're brainstorming in a group and somebody tosses out an idea and they're totally joking, you still write it down. It is amazing sometimes how an idea that somebody is just joking with ends up actually leading to some other ideas or opening up a way of looking at the problem differently. And you either write down all these ideas or you record yourself. You just record yourself talking through all the ideas, because sometimes we do a little bit better that way. And then you generate all these solutions. Consider any additional design goals. Apply your STEM principles. STEM stands for science, technology, engineering, and mathematics. Okay, so like this kind of branch of knowledge that we're working in the engineering class. And then select and justify an approach. So once you have this bank of ideas, then you need to settle on a solution that you are going to pursue. It might be the first one you came up with, or it might not be. And you need to document this, document all your possible ideas. Typically in a class like this, I would put like 5 minutes on the timer, and I would give you a set amount of time to start generating concepts. Step 3, develop a solution. Now this is where it becomes not linear. Steps 3, 4, and 5 typically overlap. Your development of the solution, the testing of the solution, your evaluating and all this tend to blur together, and you might move from step 3 to step 4 back to step 3 again, and you're going to have a real process here. Understand the iterative nature of the design process. If that's not a word you're familiar with, take a moment and write it down. It's kind of a cool word. The iterative nature of the design process. The steps can and should be repeated to reach an optimal solution. What you're going to do in step 3 is you're going to create a detailed design solution. This is going to include a sketch with possible dimensions. You're going to show maybe what you're going to build from different angles. You're going to write a description of how you think it's going to work. You're going to try to convey this idea to other people and justify the solution path. You want to be able to explain to somebody else why you chose the specific design that you chose. If a solution is found invalid or cannot be justified, the designer must return to the previous step in the design process. So this would happen if you started you picked a design solution and you started to flesh it out, and then you realize you don't have all the materials you need to pursue that solution. You thought you did, but you don't. Now you have to go back to step 2, and you have to go back to that bank of concepts that you have. Iterative means a repeated process. So it's cyclical. When you do long division, if you guys remember how to do long division, I shouldn't assume that. So you have, I don't know, 600, it's been since March since I tried to do this, and I'm no good at it. 653 divided by 2. You would go through this process. How many times does 2 go into 6? You write the quotient up top, bring it multiply, bring down, subtract, bring down the 5. And then you repeat the process for the 5, and then you repeat the process. That's what we mean by iterative. So when they talk about the iterative nature of the design process, what they mean is you develop a solution, you're going to evaluate this, test the solution, evaluate it, and then you're going to go back and make revisions to your solution. You're going to talk about how it could be improved. You're going to make adjustments maybe to your problem or to the constraints that you have. And you're going to kind of keep going around in a circle, improving on your solution all the time until you run out of time to do it. Step 4, construct and test. This is where students usually want to jump to, because this is where it honestly gets fun. Your group should consider how you will test your final prototype in the design phase. A prototype is typically like a smaller model that gives somebody else an idea of how your design would work. In our instant design challenge it's pretty much building your design. The design will evolve over the prototyping phase. So you're going to construct your design. You've generated the concepts, you've fleshed it out, you've drawn a picture, you've described how it's going to work. Now you need to actually try to put it together. Be advised, it might fail. Okay, and that's okay if that happens. So in this class, we're going to learn how to build stuff that doesn't work and to not get discouraged. We're going to go back. Plan prototype testing to ensure performance, usability, and durability. Then you're going to test your prototype and collect and analyze your data. We're going to use data to justify whether or not our solution is good or worth keeping. In the example with the bridges, students tested it by building it and then measuring how long their bridge was. And they got really creative with how they held it. In fact, some of them were held together with spit. Not making that up. They found a way to like spit on the paper, which last year was maybe okay, but with COVID, we are not going to spit on the paper. I don't even know if we do that activity, but no spitting. Okay, don't do it. If a testable prototype cannot be built or the test data analysis indicates a flawed design, the designer must return to the previous step of the design process. So you end up going back. Maybe you need to revise your concept. You need to adjust stuff. You thought the glue was going to hold, or you thought the paper clip or the rubber band was going to work, and it turns out it doesn't. So you have to adjust your design. You might even have to go all the way back to step 2 and try a totally different concept. And that is okay. That's that iterative process where we keep going back. Like I said before, it's not linear. Step 5, evaluate your solution. So remember I said, we want your solutions to work. Like we really do want them to work, but they won't always, or they'll work to varying degrees of success, and we want to be able to evaluate that. So based on testing results, you may have to face some tough decisions about next steps. If the results of the test indicate that the design does not meet expectations, you may have to return to the previous step in the design process to rethink and revise the design. That could be just going back to the testing phase. I did one in my training. I forget what we were doing. It was something similar to what you're going to do. We had to launch something. And in our testing phase, my partner that I was working with, he was doing the launching and I was doing the measuring. And he realized about halfway through that if he held the device a certain way, he could get more consistent results. And so that would be an example where you might just have to go back and just do the testing part again because you realize the way you tested it was flawed. You might have to go back to the building, the design or the concepts, and it's okay. You're going to keep doing it until Miss Taylor calls time. Okay. You might have to evaluate the solution effectiveness, reflect on the design, and recommend improvements. And all of this should be documented in your engineering notebook. So you're going to actually write down the thin rubber band didn't work. We think a thick rubber band would work better. And then redesign the solution if necessary. If the solution does not solve the problem, the designer must return to the previous step. And I think I've kind of pounded that to death. Okay, step 6, presenting your solution. So this is where those of you that are really shy very much struggle, but it is a part of engineering and it's a part of life to be able to present yourself well and present the work that you've done. We're going to keep it friendly. I think I'm a pretty non-judgmental person. I'm not going to put undue pressure on you as long as you're doing your best. So presenting your findings is a great learning opportunity. An effective presentation of a design proposal is a critical step in the design process. It must clearly state the main points and precise details that enable a product to evolve from an idea to the marketplace. Your presentation can take the form of documenting the project, that would be in your engineering notebook, and communicating the project. And we'll be creative in some of the ways that we go about communicating the project, especially where we're hybrid and you're going to be doing some of this work at home on your own. Product improvement or redesign will require the designer to repeat the design process. And if you think about like the technology that we have, you can see this. If you have an iPhone, pretty much every year they will come out with a new model. And that's because they're constantly going back. What can we add? What can we improve? How can we make it faster? How can we add more memory? How can we have different apps? Like we're constantly revising. As a teacher, this is my second year teaching IED, and so I'm very much at the beginning of the process. I am in my 10th year teaching Algebra 2, and it's a lot more refined. So if I have you for Algebra 2 or have had you in the past for Algebra 2, or you get me in the future, you would see that it's a lot smoother, and that's because I've gone through that process more times. It's just how life is. Okay, this is really small, so I apologize for that. What does each step look like in terms of what I should produce? So for those of you that are really grade conscious, you're probably wondering, well, how is Miss Taylor going to know if I did X, Y, and Z? How is she going to know if, what do I need to produce? Now, just as like a provision here, it's not going to look the same for every activity we do. When you're doing work on the computer, it will look different from when you're doing what we call an instant design challenge. Things that run more like labs where you have to take measurements will look different from our final project of the year, which will be much more involved and have a lot of different components to it. So you always want to be listening, make sure you're writing stuff down. One advantage of doing what we're doing with the hybrid is that everything is being digitized as well as being done in person. So if you forget this presentation, unlike if we just did it in class and you slept halfway through class because it's at 7:15 and then you don't remember anything, you actually have the ability to go and pull this video again and listen to it again. If you've been absent, you're not going to fall behind. And so you want to be paying attention to what the requirements are, but you'll be able to look them up if you need to. Just don't keep asking me over and over to keep repeating them, because I won't like that. So for step 1, defining the problem, the word here is the word deliverables. That refers to what you might have to deliver, okay? And it can change. So in step 1, you might need to deliver what's called a design brief, which is a written plan that identifies a problem to be solved, the criteria, constraints. The brief is used to encourage thinking through all aspects of the problem before attempting a solution. You have to know what you're trying to do before you will be able to successfully do it. In that part of the process is where I need you guys to ask me questions. So you're looking at the task, you know what materials you have, you're going to have questions. Ms. Taylor, can we, cut the yarn? Are we allowed to, if we have a plastic cup at home, can we use that? You're going to want to ask those questions. Is it okay if I just throw the paper ball? Probably not, but you're going to ask that. We want to clearly define what the problem is, what the requirements are, so that you know what it is you're trying to do and whether or not you've met the goal. Generating concepts. If you have to deliver anything, typically for this, I might want to see evidence of your brainstorming. What they have there is something called the decision matrix, which is a tool used to compare conceptual design solutions against one another using a specific criteria. So it looks something, a matrix is just an array of numbers usually. Used to cover matrix math when I taught a class called analysis, but you might have something like this. You might have, that's a P. PowerPoint is not the best program to do this in. So you might have something like price, the amount of time it takes to build. You might have, I don't know what else, like size might be a requirement. And what you would do in a design matrix is you would look at your first concept, your second concept, your third concept. And what you would do is you would rank them. Like basically cheaper is better. So you would rank them and assign them a point value. How much time it takes. You would rank them, from the best to the worst, and size. Nobody wants a cell phone that's the size of a briefcase. Okay. That would not work. And so you would rank them based on what the product was, and then you would add up the numbers from your rankings, and you would make your decision based on which one had the best number. In other words, it would be the best balance between price, time, and size. It could be other things like accessibility of materials and demand in the marketplace. There could be all kinds of things, but that's what a design matrix is. We might do that for some of the projects. It won't be something we do all the time. Develop a solution. So things that you might need to do, I'm going to home in right on that section down there, would be technical or construction drawings. We are going to learn how to do technical drawings and orthographic projections in this class. Maps, flow charts, electric circuit schematics. We won't do that in this class. I don't think, maybe at the end if we get that far. But the third course in this series is supposed to be digital electronics, and I'm supposed to teach that if I can get the training this summer, and we would do all kinds of circuit schematics in that. It's fun stuff. Other often graphical models are produced using computer or software. So that is something that you could produce for your solution. It could be a handwritten sketch, a computer generated sketch, flow charts. It can be annotated with written descriptions where you're going to convey what your solution is going to look like. For construct and test a prototype, you would produce the actual model. So you would sit in class and you would put together whatever it is that you were putting together, or you're going to build it at home. And then your test report, because you're going to test your model and then develop a report with some data analysis. So for this first one, you're going to be doing a box plot for it, sometimes called a box and whisker plot. So that's what you'll be working on for this, but that's what your constructing and testing would look like. For evaluating the solution, you would make recommendations for optimizing the design or improving on it. You'd give some kind of an assessment of my design was successful because, or my design was a total flop because whatever. And then you're presenting your solution. It can a formal presentation, a process of sharing carefully planned information to an audience, or a project portfolio, and that would be the written version of that. One of the ways that I would like you to present your designs is going to be using Flipgrid. I used it a little bit last spring and I loved it. It's a great way to do the presentations in the comfort of your home. So you don't actually have to physically look at your classmates. You can blur out your face if you want to. So if you're very self-conscious about what you look like, and I'm self-conscious, I hate looking at myself in videos. I hate listening to myself in videos too. That's going to be tough about this hybrid thing. And presenting your solution that way. And then you guys can actually see the other presentations. You can see what your classmates did. And it doesn't take up class time because presentations tend to take up a lot of time in class. So Flipgrid is great. If you have done Flipgrid before, I would like you to go to the class discussion board for IED, so your period 1 class discussion board, and I would like you to just write in the class discussion board, yes, I have used Flipgrid before. And then, if you hate it, feel free to write that too, or if you loved it. I'd like to get an idea of how many of you have used Flipgrid. It is available through like a desktop or laptop, and there's an app that you can download for it as well. And if you're not familiar with it, it's a way of creating like a classroom and a class assignment, and then everybody can record videos, and the videos upload like to a big grid, and then you're able to interact with each other with the videos. It's pretty cool. All right. And so now what? This is the last slide. We're almost done. Now what? Where do we go from here? So today's lesson, all about the design process, a little bit dry, but it does set us up for what we're doing next. Now that we've covered the basics of the design process, the next step is for you to get a chance to practice it. So what we are going to do next class, that I see you, I guess I'm recording this for Friday the 21st, so is Monday the 24th. That is a face-to-face class, 7:15 a.m. I can say like I'll see your bright and smiling faces, except I won't see if you're smiling, which is a shame. Hopefully you'll be smiling. What we're going to do on Monday is I'm going to present the problem to you. You're going to be building a catapult-like device to launch a small foam block. We'll discuss the constraints. I'll distribute the materials. I have everything except the rubber bands. I should have those sometime tomorrow though. So I'm basically going to give you a bag that will have the materials that you're allowed to use in it. Just be advised, some of the bags have holes, so the paper clips might fall out. If that happens, we're going to roll with it. And then in class on Monday, we're going to complete steps 1 and 2 in the design process. So we're going to talk about the problem. I'm going to let you guys ask me about the constraints. Some of the things you might want to talk about or think about is, are you allowed to modify the materials? So I'm giving you a paper cup. Are you allowed to slice and dice and turn inside out your paper cup, or do you have to use it as given to you. Sometimes the answer to that will be yes, and sometimes it will be no. You probably also want to know if you're allowed to use anything else from home that you might have. And sometimes the answer to that will be yes, and sometimes no. On Tuesday, the 25th, we'll be meeting virtually. Make sure you meet at 7:15. What I'll do on Tuesday is I'm going to outline the agenda, and then I'm going to release you to complete the activity and gather your data in the remaining time. So we will not be in a live meeting for the full 50 minutes like we are today, or close to the 50 minutes. We're going to come online. I'm going to tell you what I expect you to do before 8:05, and then I'm going to end the meeting, and you are going to be free to complete the activity and gather your data in your living room. Now, what I will do during that time is kind of what I would do if we were in class. If we were doing it in class, I would tell you this is what you're supposed to do in class period, and then I would release you to do it, and I would monitor your progress. I'd ask if you had any questions. So the way that's going to look virtually is I will be available live on the Help Center to answer questions or do a one-on-one meeting with you as needed. So as you're working at home, and I wanted to do this from home because in class with all the desk shields, we really don't have mobility for you to test your catapults. Like we can't move around the room enough. So you'll be able to do that at home. But if you have questions as you're working, which will probably happen, you're going to have something that doesn't work out right, or a material that broke and you broke one of your popsicle sticks and you don't know what to do, or you're not sure about how you should measure your data, that kind of thing. I'm going to be still live on Teams. I'm going to sit at my desk. I'm not going to go anywhere. And I'm pretty much going to wait for you guys to type in your questions. So we're going to end the meeting, but don't log out of Teams. Stay in Teams so that you can ask questions. And then at 8:05, we'll be done. Hopefully that'll be plenty of time for you to complete the activity, and then you'll be done. Wednesday, the 26th, is another virtual meeting. We are going to meet at 7:15, and it will be kind of like this. I might do it in a different program that's easier for me to write in. I can't write in PowerPoint very well. But we're going to do a lesson on box plots, also called box and whisker plots. And I'm going to show you how to make them. If you're a student in Algebra 2, we cover box and whisker plots later in the year, so consider it ahead, like a advanced math. You can also do them on graphing calculators, so I might do a bonus session on that. But we'll go over box plots virtually on Wednesday. Next Thursday, I will see you face to face again. One of the things I want to do is do a quick check of your box plots, and then we're going to complete step 5, which is that evaluating your solution. You're going to decide whether or not you've got a good design, a bad design, and make recommendations for how you could improve your design. And then next Friday will be virtual again. We're going to go over how the designs will be presented, and then I'm going to release you to create your presentation videos. I'll probably give you some options. So Flipgrid will be an option. And I might give you the option of just like recording a video on your phone or recording a video in Teams. So what we can do is I can meet one-on-one with you in Teams during class on Friday. And the presentation won't be a big deal, probably 2 minutes at the most. And you're going to talk about how you built your design and what your data looks like and whether or not it was a good design. So don't stress out over it. As long as you do the project and not somebody else, you should be able to talk about it for 2 or 3 minutes. It should go by okay. And I think that's it for this lesson. So according to my PowerPoint timer, we are at 39 minutes. So between the intro to class and any Q&A afterwards, I think this is Friday. If we're live, then I'm playing this in a live session. So I'm going to stop the video and we'll do Q&A. If you're doing this through a link, then once the video is done playing, you are done. There is no new homework for the weekend. So you don't need to do anything for this class. Just go back and rewatch the video, make sure you know the design steps. Other than that, have a fabulous weekend, and I will see you all on Monday.